Swayam Prabha. Digital India. Educated India.
Okay, welcome everyone. We'll continue with our topic of optimization. If you remember, we were previously studying what is called real analysis. Real analysis is a careful study of real numbers, okay, and real numbers and their associated properties. So we studied the following topics so far. We've defined what a sequence is. We defined what it meant for a sequence to be bounded. So we defined a bounded sequence. We defined what it means for a sequence to converge. So all concepts related to convergence. What it means for a sequence to converge, what it means for a sequence to not converge, and what the limit of a sequence is. And from that we also defined what is called a subsequence. These were the 4 topics we covered so far in real analysis. Now let me take off from here. So it's very easy to see that if a sequence converges, then every subsequence of that sequence converges. Every subsequence of that sequence converges, and it converges to the same limit. It does so to the same limit as the original sequence. Right? Now, can you tell me if the converse of this statement is true? So, if every subsequence of a sequence converges, then does the original sequence itself converge? Yes, no? Yes, okay. Someone saying yes. Why yes? Okay, that's the correct answer. So, the sequence itself is a trivial subsequence of the original sequence. So, the converse is actually trivially true. Okay, this statement is the non-trivial one. Okay, all right. Now, we were so far looking at sequences that were living in Rn. So, these were the sequence of vectors. Now, let us come down to sequences that are on the real line only. Okay, so, in that we have a famous theorem which is called the Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem simply says the following, that okay, this doesn't necessarily have to be this is not necessarily true for real numbers. So, this is true for vectors also. So, I will tell you a more general version of the same statement. So, the statement is simply this, that every bounded sequence in Rn has a convergent subsequence. if you consider sequences in Rn and make look at those sequence, if you and consider a bounded sequence in Rn and look at all its possible subsequences. Amongst all its possible subsequences, you will find at least one which is convergent to some limit. Okay. It cannot happen that all the subsequences do not converge and yet the sequence remains bounded. It is not possible. Okay. Now, this is actually a very deep fact. Essentially, what it is saying is that if you constrain the sequence to be in a box, so if you suppose here are my axes and my sequence is living in this bounded box. Eventually, it will the very fact that you are constraining it to live in a bounded box would mean that you can extract some subsequence out of this such that that subsequence eventually starts accumulating around some point. The sequence cannot dance around in such a wild manner that even its subsequences are always dancing around and never will you find a single subsequence which is convergent. Okay. So, this is actually a very useful fact because convergence of algorithms make extensive use of this particular fact. Convergence proofs of algorithms. I'll just give you a general sense about this. See, when we are computing something in optimization, what we are effectively generating is a sequence of points, sequence of iterates. You have iterate at time 1, then you go through another loop, get to the next iterate, then you get to the next iterate, then you get to the next iterate, etc. So, what you get are these is this iteration x of 1, x of 2, x of 3, etc., etc., etc. And what we want is eventually that this sequence, if you look at the limit of this sequence x of n, this limit should converge to the solution of your problem. Solution of the problem under consideration. Right. So, for example, if you are looking at this, if you want to, since we are talking of optimization problems, you want this to converge to the solution of your optimization problem. Now, to show one of the big challenges that occurs in analysis of algorithms is making sure that this actually happens. And we may often the steps towards arguing that go through you need first a way of arguing that the sequence converges at all to begin with, and that comes from Bolzano-Weierstrass theorem. You argue that there is at least a subsequence that converges, and from there you build your argument. This is you use a common way of arguing. Okay. All right. So, this is Bolzano-Weierstrass theorem. Okay. Now let me come to sequences or sets in the reals. Okay. So, now let us look at just the real line and look at suppose some set of points on the real line. Okay. So, for instance, look at the set which is the, I will just write this in words, set of positive rational numbers, for instance. So, this is the set of all numbers m by n not equal to 0, m and n m comma n both positive and they are natural numbers. Okay. So, if you look at this set, this is a set of all positive rational numbers. Okay. Now, we say that a number L is said to be a lower bound L is said to be a lower bound if it's less than or equal to all elements of S. So, now if you take S to be the set of positive rational numbers, what can you give me an example of a lower bound? -1, 0, these are all lower bounds. Right? Likewise, a number u in R is set to be an upper bound on S if the opposite is true. If x is less than or equal to u for all x in S. Okay. Now, again for the same example, set of all positive rational numbers, can you give me an example of an upper bound? There is no upper bound. Okay. Now, what we will, so if a set is bounded, if a set which is a subset of R is bounded, then does it have an upper bound and a lower bound? By definition, right? So, it does have an upper and lower bound. Why? What did we say? What did we mean by a set is bounded? We said we look at the norm of the elements in that set, and all elements should have a norm less than or equal to a prescribed number, right? So, what it means in this case, we are talking of a set of real numbers. So, the norm is just the absolute value of the number. So, the absolute value of every every number in that set is between minus m to plus m, where m is some positive number, right. So, if the absolute value is between minus m to plus m, then it means, what does this mean? So, mod x is less than or equal to m. This means that x is less than or equal to m and greater than or equal to minus m. What does this mean? For all x in S, for all x in S, what this means is that m is an upper bound and minus m is a lower bound. Is clear? So, a set, if it is bounded, will have an upper bound as well as a lower bound. Now, upper and lower bounds are not unique. If m is an upper bound, then m plus 1 is also an upper bound. Okay. Likewise, if L is a lower bound, then L minus 1 is also a lower bound. You can keep making lower bounds smaller and smaller, they will continue to be lower bounds. You can make upper bounds larger and larger, they continue to be upper bounds. So, here is another concept which is called the least upper bound. Least upper bound is the smallest such upper bound amongst all upper bounds. Okay. What does this mean? That if I take a number even slightly smaller than this least upper bound, then it cannot be an upper bound. Okay. Let me write this in English first. The least of all upper bounds what does this mean? If I, for all epsilon greater than 0, okay, there exists an x in S such that x is greater than, sorry, so I should just write this better. M is said to be the least upper bound on a set S set of R if for all epsilon greater than 0 there exists an x in S such that x is greater than m minus epsilon. So, M is said to be the least upper bound on a set in S sub, which is a subset of real numbers. If for every epsilon greater than 0, you can find an x such that x is greater than m minus epsilon. Right. So, you cannot make m even slightly smaller and still have it as a lower, as an upper bound. So, there will be at least one element whose value will be greater than m minus epsilon for every epsilon. Okay. Likewise, L is said to be the greatest lower bound on S if for all epsilon greater than 0, there exists an x in the set such that so if I increase L even slightly, then I can find an element that violates my condition. Is this fine? Okay. Now, there is a chicken and egg problem that arises in trying to define what this, trying to show that such a thing exists. The very fact that to show, if you want to show that a set must have a least upper bound, then what you need is that the set of upper bounds must have a lower bound. Likewise, if you want to show that a set must have a greatest lower bound, then it means that the set of lower bounds must have an upper bound, a smallest such upper bound, right. So, this is worked around using what is called the completeness axiom. Completeness axiom simply says that every bounded set of real numbers has a least upper bound and a greatest lower bound. So, if your set is bounded, then it does have a least upper bound and a greatest lower bound. If your set is just bounded on one side, means it is bounded above, okay, then it has a greatest, it has a least upper bound, but may not have but does not have a greatest lower bound. If it is bounded below, then it has a greatest lower bound, but does not have a least upper bound. But if it is bounded, it has both least upper bound and greatest lower bound. Okay. So, so this leads us to the definition. So now, so once you with the axiom, you know that such a thing exists. So the greatest lower bound has a name. Instead of calling it the greatest lower bound on S, we simply say the supremum of S, and it's written as this. Sorry, my mistake here. So we simply say the infimum of S. Okay. And least upper bound is called the supremum.